Recording. Okay, so we've got a circle centered at 0, 0. Radius is 5, and we're going to pick a random point, essentially, a general point on the circle, and call it xy. So I'm trying to pick one that's not an obvious point, like, straight up 5 or straight to the right 5. And since we know the radius is 5, I can label that as a 5. And then the goal is to get a relationship between x, y, and the radius. So since it's on a graph, we're probably going to draw a slope triangle in. So there's my slope triangle. And when I go to the right, I'm increasing from 0 to x. So this is just x units to the right. And from 0 to y will be y units up. And then I got a right triangle here. And if I wanted to relate x, y, and the radius, I can just use Pythag. So it's x squared plus y squared equals 5 squared. Or x squared plus y squared equals 25. And the nice thing about this is this actually is the equation of the circle. And the reason is because I let x, y be any point on my circle. It didn't have to be that specific one where I put it. I could have put it over here, and I still would have gotten x squared plus y squared equals 5 squared. So really one way to test if a point is on the circle, like let's say you looked at this one right here, which looks like it's at about -4, +3. So if you wanted to test whether or not that was on the circle, you could build a slope triangle and check to see if the radius was 5. Or you could plug it right into this equation and see if it works. So if you plug in -4 and you square it, and you plug in 3 for y and you square it, you end up getting 16 plus 9, which is 25. So that means it's got to be on the circle. If I picked a point like 0, 6 and plugged it in, you plug in 0 here and 6 there, you get 0 squared plus 6 squared is 36, definitely not 25. So that means this point's not on the circle. Okay. So this right here is the equation of the circle centered at 0, 0 with radius equaling 5. Or this one. Either one is fine. Right? So the takeaway from this is if we had a circle centered at 0, 0, but we didn't actually have a specific radius, it was just r. So the equation of a circle centered at 0, 0 with radius r, that's going to be just like this, x squared plus y squared. And instead of 5 squared, it's just r squared. So there's the main idea that I want you to get for this problem. Okay. Number 2 has you kind of work backwards in a way. It says graph the circle given by x squared plus y squared equals 9. Well, that's in this form. So that automatically means it's going to be centered at 0, 0. And the r squared is 9. So that tells us that the radius has to be 3. So if I know it's centered at 0, 0 and the radius is 3, then I can plot 3 easy points. I go up 3 to 0, 3. I go to the right 3 to 3, 0. And go down 3 to 0, -3. And I can go left 3 to -3, 0. And then you just want to kind of do your best to make a circle out of that. And there you go. And we'll label the center too, just to have it. And then that's all there is to that. Okay. If you're trying to check something like later on, we'll do a problem that says, what are the y coordinates on the circle when x is 2? So when x is 2, well, you've got this point here and this point there. So you can end up one of the methods that we'll talk about is you can end up doing a little slope triangle here where you know the radius is 3 and it's 2 across, and you can solve for this thing. Right. So anyway, we'll get there in a little bit. All right. So let's take a look at 3. So 3 is kind of like number 1. I gave you a center point and a radius, and you have to come up with a relationship between x, y, and the radius. You pick another random point on the circle and call it x, y. So our center point here is 4, 1. I'm going to pick a point on the circle and call it x comma y. And then I'm going to connect these 2 points and say the radius was 8, because that's given. And so now I'm going to draw in my slope triangle. Right there. Okay, so for a second, pretend that xy was, I don't know, it looks like it's about 8 comma, or let's go 9 comma 8, just so that it's a little different. 9, 8. So let's say it was about 9, 8 there. In order to get this, you're looking at the change in the x values. It went from 4 to 9. So this would be 5, or 9 minus 8. Right? But it's not really 9. It's really an x. So this length right here is really x minus 8. Or sorry, not 8, 4. Sorry, my bad. It'd really be 9 minus 4. So let me start over here. This, if we're looking at 9, 8, if this point were 9, 8, this length would be 5, 9 minus 4. But it's really not a 9, it's an x. So it's really x minus 4. The height right here, well, if it were at 8 and down to 1, that'd be 7, because it's 8 minus 1. But really, it's y minus 1, because it's not really 9, 8, it's y. So this height is y minus 1. So then if I said find an equation that relates x, y, and the radius, well, here it is. It's x minus 4 squared plus y minus 1 squared equals the radius squared. So this, or you could also square out the 8. So you could say x minus 4 squared plus y minus 1 squared equals 64. Okay, so this right here is the equation of a circle centered at 4, 1 with radius equaling 8. Okay. If the center instead, so the goal is to get a general equation. So equation of a circle centered at, and then for some reason textbooks always use h and k for the center point. And the radius we'll just say is r. Well, we're basically just replacing the 4 and 1 with an h and a k and the 8 with an r. So if we replace the 4 and 1 with an h and k, then this equation turns into x minus h squared plus y minus k squared equals, and then instead of 8, it's r squared right there. So this is kind of the takeaway for this. Now it turns out this is all you need, because if it's centered at the origin 0, 0, then h and k are zeros, and you end up with the equation that we got in number 1 right here. Right? Okay, so this is a huge idea for this unit right here. Right? This gives you the equation of a circle centered at hk with radius r. Okay, let's take a look at the next one. So I gave you an equation in that form. So I'll rewrite the general form here. X minus h squared plus y minus k squared equals r squared. That gives you a circle that's centered is at hk. Oops. Starting to stick here. hk, and whose radius equals r. Okay, so since it's x minus 3, you can see that the h and the 3 are the same. So the center, hk, is really 3 comma, and then this is the same thing as y minus negative 2 squared. So the k is the negative 2. So the center point here is 3, negative 2. And then r squared is 16, so then r is 4. So if we plot 3, negative 2 over 3, down 2, there's my center. Since the radius is 4, we can just go up 4 and end up at 3, 2. We can go down 4 and end up at 3, negative 6. We can go to the right 4 and end up at 7, negative 2. And we can go left 4 and end up at negative 1, negative 2. And then you just do your best to draw that circle. So there it is. Excuse me. Okay. Let's take a look at the next one. So it's another graphing the circle problem, and then we do stuff with it. So once again, I'll write the equation up here. X minus h squared plus y minus k squared equals r squared. So in this one, we have our equation. The center is the h and the k, which is really h is 3, and y plus 4, positive 4 is really negative k, so k is negative 4. Think of this as y minus negative 4 inside that parentheses. So center is 3, negative 4. The radius squared was 25, so the radius is 5. So if we plot that, let's see, 3, negative 4 is right here. And then if I go up 5, I'll end up at 1 here, and down 5, I'll end up at negative 9. And if I go 5 units to the right, let's see, 5 to the right would get me to 8. 5 to the left would be at negative 2. And so here's that circle, roughly. So there's the circle there. Okay, the other thing we have to graph is the line x equals 6. So that looks like this. It's a vertical line where all the x coordinates are equal to 6. And the question is, find the coordinates where they hit this point and this point. Okay, so you've actually done a problem like this on the last handout, on the last review packet. The only new thing was I gave you the circle. I gave you the equation of the circle instead of just some points on it so you could graph it. So one thing you should know for sure is the x value has to be 6 because it's on that green line where all the x values are 6. So really the only hard part is finding the y value. We know the radius is 5. So I know that this is 5, and I know that this is 5. And since it's on a graph, I'm probably going to use slope triangles. So if I go straight across here and then up, I got a slope triangle, and I can also go down and get another slope triangle. So when I go to the right, the x's change from 3 to 6. So that's 3 across. So then I can solve for these up and down parts, the vertical parts of those triangles. So it'd be 3 squared plus b squared equals 5 squared. And when you solve for b, I'll just tell you now, it comes out to be 4. So this is 4, and this is 4. So we were at 3, negative 4, we go 3 to the right, that makes the x 6. If I go up 4, I have to add 4 to the negative 4 and get 0. So really that's on the axis there. If I go down 4, I'm at negative 4, I subtract 4 more, I'm at negative 8. So that's one way to get these 2 points, 6, 0, and 6, negative 8. So that's one method. So I'll show you another method right here. Right. So here, I'll kind of draw it over here too so that you have it in your notes. So this was 3, negative 4. This was 3. We solved for b equal to 4. B equal to 4. These were 5. And so then this point ended up being at 6, 0. And this point ended up being at 6, negative 8. So this I'll describe as method 1. Method 2, we have a second method now that we can use because we have the equations. Right? So this is the new thing, and so that it creates a new way of solving this type of problem. If I only care about when x is 6, and I know that the equation of the circle has an x in it, then I can just plug in the 6 for the x. So plug in or substitute 6 for x. So if I do that, we got 6 minus 3 squared plus y plus 4 squared equals 25. So then as I work this out, let's see, that's going to be 3 squared, so that's 9, plus, and then y plus 4 all squared equals 25. So then that's going to be y plus 4 squared equals 25 minus 9, which is 16. And now I can take the square root of both sides. You could FOIL it out, get the 16 over, set it equal to 0, and then use quadratic formula. But you can also just take the square root of both sides at this point. Now, in this case, think of it like this. If I said x squared equaled 25, when you take the square root, in class, most of the time we've just been saying, well, that equals 5. But that's because we're typically talking about the length of sides of a triangle. You know, if this is x, then the negative, really, it's plus or minus 5, but we throw away the negative every time in this class because I'm talking about how long the side is in a triangle, and negative 5 doesn't make sense. But if you take negative 5 and you square it, you get positive 25 still. So both of those answers actually work. So as soon as you take the square root of both sides, technically what you're supposed to be doing is plus or minus. Right? So because if something squared equaled 16, the something is either 4 or negative 4. So really right here, we have plus or minus 4. And then I got to get that 4 here out of the way, so I'm going to subtract it over to the other side. So it's plus or minus 4, minus 4. So it's really two answers. Y equals positive 4 minus 4, which is 0, or y equals negative 4 minus 4, which is negative 8. Remember, that happens when 6 is x. So when x is 6, you get 6 for x and 0 for y, or you get 6 for x and negative 8 for y, which are the same two answers we got over here, right? Okay, so you get to choose whichever method you prefer. I will tell you, it seems like when students choose this algebra method instead for method 2, this is the part where they mess up. They forget that plus minus all the time. And if you forget it, you only get one answer. Okay, let's take a look at number 6. So we got the diameter of a circle with endpoints at 4, negative 2, and 6, negative 6, 10. So I'm just going to draw the circle here. I'm not going to bother with axes. Let's see, 4, negative 2 would be like down here somewhere. Negative 6, 10 would be way up over here somewhere instead. And then it's a diameter, so we know it's got to go through the center of the circle. Okay, so the center is the midpoint of that segment. So to get a midpoint, you could average the x's and the y's. So it'd be negative 6 plus 4 over 2, and 10 plus negative 2 over 2. So I'm just averaging the x's and averaging the y's. If you work that out, you get negative 1. Let's see, negative 2 over 2 is negative 1, and 8 over 2 is 4. So the center point is now negative 1, 4. The other thing we need is the radius in order to write the equation of the circle, because remember, it's going to be this. And we already know the h and the k are negative 1 and 4. So now we need the radius. To get that, we can just build a slope triangle here. And when I go across, the x's change from negative 6 to negative 1, so that's 5 across. And I drop from 10 to 4, so that's 6 down. By the way, if you'd done the slope triangle over here, you would have still gotten 5 and 6. So then to solve for r, we'll just do 5 squared plus 6 squared equals r squared. So that's going to be 25 plus 36 is 61 equals r squared. And then I'm not even going to bother square rooting it because I want r squared. I don't actually care what r is. I care what r squared is. So the equation of the circle is going to be x minus negative 1, so x plus 1 squared, and then plus y minus k, and the k is 4, equals r squared, which is 61. So there's the equation of this circle. Okay. let's take a look at the next one. Where is the next page? Kind of lost it here. Let's see. Must be buried underneath here. Hold on. I'll pause it. Okay, I fixed it. All right. So here's number 7. So this is a different topic here, really. All the other problems had to do with graphing circles. This last page here is a new idea. So it's we've dealt with angles inside a circle, but now we're dealing with what happens if you have these lengths given to you inside a circle. So in this one, it says use similar triangles, but we don't have any triangles yet. So if I actually create a couple triangles, I'll connect this one. And let's do this one. So remember, the main way to get similar triangles is through AA. You match up a pair of angles. One pair of angles is already pretty obvious. These vertical angles are congruent. Another pair of angles that matches up, this angle right here, if you look at the arc it carves out, it's this one. Well, there's another angle in the picture that carves out the same arc. It's this angle. So if we knew how big this arc was, you would just cut it in half to get either of these two little angles over here. Right? Similarly, if we look at this arc, that's the inscribed angles that carve out that one. If I cut this in half, I get this angle, and I get this angle too. So now we have more than AA. We actually have AAA. So we've done even better. All right, so then it's just setting up proportions once you have similar triangles. So if I set up a proportion, the 5 right here is between the 1 and 2 tick marks. So that goes with the 4, because that's between the 1 and 2, curves. So 5 goes with 4 in the same way that the x here goes with the 8 here. So then you cross multiply and divide by 4, and you get x equals 10. All right. So we're going to do the same thing on this one down here. Let's see. Why don't we connect them a little differently this time? Let's do this one and that one. Okay. So if we match up some angles, we definitely know the vertical angles match up. I know that this angle on the top left opens up to this arc right here, but so does this one down here. And they're both inscribed, so they're both half of whatever that arc is. And then you can do the same thing with this arc and these angles. That one is half of the arc, and this one is half of that arc. So now it's just a matter of matching stuff up. The A in the top triangle is between the 2 curves and the 1 curve, so that goes with D. The same way that C in the top triangle has to go with B. And then when you cross multiply, you get A times B equals D times C, which is the same as C times D. Okay. So let's take a look at number 9. So show that ACD is similar to ECB. So this one's a little tricky because those triangles overlap. If I connect ACD, AC is already there, and then to D, and then back to A. So there's one of my triangles right here. Right. ECB is this one. It goes E all the way to C, and then to B, and then back down to here. Right there. So let me draw those by themselves. So here's A, C, and there's D. A, C, D. And then the red one looks like this. B, C, E. Okay. We're trying to go for angle again, since we have no side lengths. So we're going for AA similarity. So one of the angles that has to match up in these 2 triangles is angle C. Notice it's reflexive. So C equals C, right? Another one that matches up, let's see here. If you look at angle E down here, that's half of BD, right? But so is this angle. A also carves out that arc, and it's also inscribed, so it's half of BD as well. So this angle has to equal this angle. And so since those two angles are the same, the third angles would match up too. So I'm just going to put a dot there instead of 3 curves. Okay, so then let's see. We need to use these 4 sides in our proportion now that we know that they're similar. So AC, this side, is between the 1 and 2 curves, so it goes with CE, or EC. So AC goes with EC. The same way, let's see, what's another side that we have? DC. So DC is between the dot and the 1 curve. So that goes with BD. Did I mess that up? Oh, sorry, BC. Sorry, not D. I'm misreading my own. That's a D. So let's see here. What did I say? DC goes with BC. So when we cross multiply, we get AC times BC equals EC times DC. Whoop, lost the C. There it is. Okay. So there's a way. Let's see here. Let's take a look at this next one. Use the results of number 9. Okay. This one, the way to look at this is a little different. Let me erase this stuff that's in the way here from the original diagram. Notice all of these segments are parts of the original diagram. So it's really AC, which is this whole length right here, times BC, which is just the outer part of that segment. So we did the whole thing times the outer part. And then down on the bottom chunk, we did EC, which is the whole thing here, times DC, just the outer part. So if we use that kind of logic down here, we could do the whole part here, which is 25, times just the outer part, which is 13, equals the whole thing here, which is 15 plus x, times just the outer part, which is 15. So 15 plus x times 15. So if you work that out, this side's 325 equals, and then if you distribute, you get 225 plus x, or 15x, sorry. And then you subtract the 225 and you get 100 equals 15x. And then you divide by 15, and it's 6.6 repeating equals x. Okay. So that's actually the last major idea in the unit. If we look down a little bit below here, there's a trick that students have come up with in the past to remember that idea. Now up here again, what we did was we took the whole segment times just the outer part, the part outside the circle, and then did the whole segment times the outer part. So students several years ago came up with, they called it the Wo-Wo theorem, because it was the whole times the outside part equaled the whole times the outside part. So in your textbook, that shows up this way. I'll use the same letters that the textbook used. So they called this long part R, and this part S, and then down below they called the whole long part T, and the outer part U. And so then they ended up with R times S, so the whole times the outside, equals T times U, the whole times the outside. So I'll do whole times outside equals whole times outside. Okay. In this next one, it's still the same kind of idea, but notice this, so what I did was, it's a progression, these 3 pictures. This stays the same in all 3 pictures, right there. It's the bottom line that kind of moves out, so you can kind of see right here, it hits the circle fairly into the circle, then it starts to move out a little bit more, and eventually, it's just tangent to the circle right there. But the formula stays the same. So right here, the whole thing is still r. The outer part is s. Here, the whole thing is t, and the outer part is u. And it's still whole times outside equals the whole thing times the outside. Down here, something else happens. The whole thing is r, and the outer part is s. Down here, the whole thing is t, and the outer part is also t. So t and u in this case are the same thing, right? So it's really just t. So if we say the whole is r times the outside is s, so whole times outside equals whole times outside. Well, the whole thing down on the bottom chunk here is t, and the outer part is also t. So now you end up with r times s equals t times t, or t squared. Okay? So then let's do number 11 so you can kind of see how this creeps up in problems. Solve for x in the diagram below. Well, it's one of these things where those segments are sticking outside the circle, so we're going to use that whole times outside equals whole times outside. Okay, so let's look at the 10. Right? The 10 is the whole segment and the outer part of the segment. So it's just 10 times 10. And then this segment here, the whole thing is 3x plus x, which is 4x. So the whole thing there is 4x, and the outer part is x right here. So then we got 100 equals 4x squared. So if I divide by 4, I get 25 equals x squared. And then take the square root, and you get 5. So x is 5 there. By the way, really it's plus or minus 5, but then since we're talking about a length, you throw away the negative. Right? Okay, I hope that helps a little bit. And that's the entire unit's worth of notes there, actually. So all the rest of the stuff is going to be homework and review stuff. All right, okay, I'll see you guys soon.